The work of Nobel Prize has transformed our understanding of the world. While approaching the Nobel Prize winners in chemistry, we not only learn their achievements, but also the spirit of honesty, tenacity, innovation, and forging ahead.
Hello everyone, welcome to today's class, Approaching Nobel Prize Winner in Chemistry. 大家好，欢迎走进今天的课堂，诺贝尔化学奖。Today I will introduce you Daniel Shechtman for the discovery of quasi-periodic materials. I think you all know about mosaic because they are beautiful and charming. In 2011, the Nobel Prize Committee for Chemistry used the term fascinating mosaic in the Arabic word to describe Shechtman's discovery. Let's take a look. Dan Shechtman won the Nobel Prize in Chemistry in 2011 for the discovery of caustic crystals.
Let me take you from the stars down to Earth, from the telescope to the microscope. And these are two extremes, but you will find my talk comprehensive, I hope. So there were three surprising discoveries in the mid-80s that more or less shook the world in a way, and they brought three Nobel Prizes, and the last one is here. Although the first discovery, chronologically, was that of quasicrystals, as you see here, and the names on that are my name is Ilan Blech, Denis Gratias, and John Kahn. I'll tell you about them later on. Then came Fullerene by Kroto and his colleagues in 1985, and in 1986, high-temperature superconductivity.
Dan Shechtman was born in Tel Aviv in Israel. He obtained his PhD in materials science from the Israel Institute of Technology. Dan Shechtman has been associated with the institute since that time, but has also spent time abroad. He made his Nobel Prize awarded discovery at Johns Hopkins University in the early 1980s. In the majority of solid matter are crystals. Atoms are organized in the ordered pattern. Physicians believe that the structure of all crystals consisted of patterns that repeated over and over again. In 1982, when Dan Shechtman was studying diffraction patterns, which occur when X-rays are passed through the crystals, he discovered a regular diffraction pattern that did not match the periodical repeated structure. This showed that there are crystal structures that are mathematically regular, but that do not repeat themselves. These are called quasi-crystals. As we can see from this picture here, they have very beautiful structures. In 1982, while on sabbatical at the National Bureau of Standards in Maryland, Shechtman was investigating the properties of aluminum iron and aluminum manganese alloys for research programs. Shechtman and his colleagues mixed the aluminum and magnesium in a roughly 6:1 proportion. They then heated the mixture, and once they melted, rapidly cooled it back to the solid state. Using an electron microscope, Shechtman found that the solidified alloys unexpectedly displayed five-fold symmetry. That is, rotation at by 72 degrees produced the same structure. Such a symmetry was considered impossible in crystals, since it could not provide a basis of repeating regular structure. The alloy structure did not repeat. Shechtman was verified to consisting that he has discovered a crystal with five-folded symmetry and aperiodic structure. The type of possible structures in crystal has been considered a close subject since then. Shechtman was asked to leave his research group at the National Bureau of Standards, and it was not until 1984 that he was able to publish his findings. Later that year, some American physicians used the term quasi-crystal to describe Shechtman's discovery. Ever then, few scientists were convinced. American chemist Linus Pauling was particularly fierce. He said, "There are no quasi-crystals, only quasi-scientists." 3 years later, Shechtman was convinced by scientists in France and in Japan. They made quasi-crystals that were large enough to examine it with X-rays. An image has rotational symmetry if there's a center point around which the object is turned to a certain number of degrees, and the object still look the same. That matches itself a number of times when it's being rotated. As this picture shows here, the poker, three-folded triangles, five-folded flowers, and six-folded pizza. And also, the order of carbon atoms in diamonds periodical. The allowed rotational symmetries are 1, 2, 3, 4, and 6. Five-folded rotational symmetry as well as many other symmetry beyond 6 is forbidden in periodic structure. This is Shechtman's NBSTEM logbook. It records the first observation for 10-fold or 5-fold symmetry. This is the picture of the first view of the isochondral phase. Electron diffraction from the isochondral phase have five-folded rotational axes, and it's not periodic. The ratio of distance between the central spot and the other spots is Fibonacci number, also known as golden mean. There are 10 twins in an iron and aluminum intermetallic compound. Each twin diffracts like a single crystal, but the supercomposition of all 10 patterns results in a super five-fold rotational symmetry. This is the X-ray diffraction pattern that convinced the committee of crystallographers that five-folded symmetry can exist in crystals. This became available only in 1987. Only electron diffraction patterns were taken before that time. Now you may ask, why QCS were never discovered before 1982? Are they very rare? Are they not stable? Are they difficult to make? No, QCS are not rare, and there are hundreds of them, as the table shown here. Many of them are not stable and transform to periodic structures at high temperatures, but QCS can be thermodynamically stable. Examples are shown here. QCS can be made by many manufacturing techniques, such as casting, rapid solidification, single crystallographs, and electron position, and CVD and PVD. So why QCS were never discovered before 1982? I think because of the 5 aspects. First of all, transmission electron microscope is needed, and professionalism, tenacity, believing in yourself, and courage are needed as well. So what's your opinion? Please leave the message after class. Thanks for listening.
大家好。诺贝尔化学奖评审委员会在颁奖词中用阿拉伯世界中迷人的马赛克镶嵌画来比喻谢德曼的发现。谢德曼在1982年发现了晶体铝过渡金属合金的20面体物象，从而提出准晶体。虽然在原子层面进行复制，但在原子之间相互结合的模式上却从不重复。在这一发现以前，科学家们一直以为晶体内的原子结构是不断重复的。谢德曼的这一发现当时是极具争议性的， 为了捍卫自己的发现，他甚至曾被要求离开研究小组。诺贝尔化学奖评审委员会说，不过他锲而不舍的努力最终迫使科学家们开始重新考虑他们对物质本质的认识。其实，在发现的最初阶段，谢德曼自己也觉得难以置信，不可能有这样的物质存在。谢德曼对自己说，在记录这一发现的笔记本上，谢德曼一连标记了3个问号。不过，现在他的发现已经使得准晶体成为物理学家、材料学家、数学家以及晶体学家的重要研究领域。好了，本次课到此结束，谢谢大家，再见。